Section: Introduction. In this section, we discuss the development of AI assistants that can effectively interact with people in shared spaces and follow their instructions, which could greatly enhance assistive robotics and reduce household labor. To achieve this, we need to tackle the challenge of converting natural language instructions into actions that robots can perform. Traditionally, this has been approached through grounded language learning, which connects abstract language to specific actions. However, these methods often overlook a key aspect: the ambiguity present in everyday human communication. Humans typically assume that their listeners have prior knowledge, which can lead to incomplete instructions. For instance, when a person asks a robot to pass that from the sofa while tidying up, the robot cannot fully understand the request without additional context about the person's intentions. By observing past actions, like putting books into a box, the robot can infer that the person likely wants to store the books in that box. The ambiguity in instructions arises from two main factors: the assumption of shared knowledge about intentions and the trade-off between clear communication and efficiency. We focus on scenarios where a human and a robot collaborate, with the human providing natural language instructions for specific tasks. Previous methods often treated the human as a mere source of commands, neglecting their role as an active participant in the environment. To address this, we introduce a new framework called Follow Instructions with Social and Embodied Reasoning, FISER. This framework emphasizes the importance of explicitly incorporating the human's intentions into the model. We break down the problem into two parts: social reasoning, which predicts the subtask the human needs help with based on context and past actions, and embodied reasoning, where the robot plans and interacts with the environment. To improve the robot's ability to follow ambiguous instructions, we add a plan recognition stage that uses logical predicates to infer the human's overall plan. We implement a transformer-based model trained to predict subtasks and the human's intentions at various stages. This step-by-step approach contrasts with the typical end-to-end methods used in prior research. We test our hypothesis using the HandMeThat (HMT) benchmark, which presents complex instruction following tasks in a household setting. HMT includes many physical objects and actions, making it a challenging environment even for advanced language models. We also create a chain of thought (COT) approach to prompt GPT-4 based on our framework. Our experiments yield two significant findings. First, models that separate social and embodied reasoning using the FISER framework outperform traditional end-to-end models, highlighting the value of intermediate reasoning about human intentions. Second, training smaller models from scratch on this task surpasses the performance of large pre-trained models using COT prompting, suggesting that pre-training alone is not enough for success in these complex tasks. We analyze the limitations of GPT-4 Turbo to understand why leading language models struggle with the social and embodied reasoning required for these tasks. In summary, our contributions include the FISER framework, which enhances instruction following by first clarifying human requests through social reasoning and then determining actions through embodied reasoning. We also introduce a human plan recognition stage to improve performance in complex scenarios. Our FISER models achieve an average success rate of 64.5% on the HMT benchmark, setting a new state-of-the-art. Our open source code is available for further exploration. Section Summary. In this section, we introduce the Follow Instructions with Social and Embodied Reasoning, FISER, framework, which enhances robot instruction following by explicitly modeling human intentions through social reasoning and a separate embodied reasoning phase. Our approach demonstrates improved performance on ambiguous tasks, achieving a 64.5% success rate on the HandMeThat benchmark, and highlights the importance of understanding human context and intentions in collaborative environments. Section: Related Work. In this section, we discuss related work in grounded language learning, collaborative communication, goal recognition, and reasoning with intermediate steps. For grounded language learning, we recognize that for AI to be effective in our homes, non-experts must communicate with AI using natural language. Researchers have focused on how to connect natural language to specific meanings in our physical surroundings. Some studies have looked at how language can guide task completion in certain environments. With the rise of large language models, LLMs, many have explored how to ground language using these pre-trained models. A notable example is Say Can, which assesses how likely a robot's subtask will help achieve a broader goal. However, these studies often rely on clear human intentions in their instructions. For instance, Say Can easily interpret the instruction, "I spilled my Coke, can you bring me something to clean it up?" because the sponge is the only cleaning tool available. In contrast, we tackle the challenge that real human instructions often leave out details for efficiency, leading to ambiguity that requires us to infer intentions. In terms of collaborative communication, we examine scenarios where humans and robots share an environment, which relates to existing literature on this topic. Some works, like Cereal Bar and Dial Fred, involve humans giving instructions while possibly responding to the robot's questions. We, however, focus on how the AI assistant must interpret both explicit messages and the implicit cues from human actions. We assume that instructions are not fully detailed but are a balance between being informative and minimizing communication costs. We emphasize the HandMeThat benchmark, which requires understanding both explicit and implicit messages when following unclear instructions. Previous work on this benchmark relied on predefined structures and extensive domain knowledge, which may not apply in real-world situations. Regarding goal recognition, we aim to deduce human intentions from their past actions. Most research in this area assumes that agents make nearly optimal decisions toward their goals at every step. Understanding human intentions in physical environments has been explored, such as in Watch and Help, where AI infers goals from demonstrations without using natural language. Some recent studies have utilized LLMs for goal inference based on observed actions or messages. In our approach, we use a small language model trained from scratch to assist in this reasoning process, focusing on social reasoning rather than precise goal recognition. Our work is also inspired by research that employs intermediate steps to tackle complex reasoning tasks, including formal reasoning and program synthesis. Studies have shown that predicting intermediate steps can yield better results than directly predicting final outcomes. We demonstrate that social reasoning tasks also benefit from this method, highlighting that inferring human intentions is vital for effective human-robot collaboration. Finally, we formulate our problem as a human-robot Markov decision process, which includes states representing objects and agents, a joint action space for both human and robot actions, and a transition function that defines how actions lead to new states. We consider a scenario where the robot follows a single round of instructions. Starting from an initial state, the human interacts with the environment while the robot waits. The human eventually provides a natural language instruction asking for help. Given the trajectory of actions and the final state, the robot must take a series of actions to maximize its rewards over time. Section Summary. In this section, we discuss the challenges of grounded language learning for AI, emphasizing the need for robots to interpret ambiguous human instructions in collaborative environments by inferring intentions from both explicit messages and observed actions. We also outline our approach using a human-robot Markov decision process to enhance goal recognition and social reasoning through intermediate steps, ultimately aiming to improve human-robot collaboration. Section: Modeling the human's intentions. In this section, we explore how to model human intentions in the context of human-robot interactions. A simple approach to the human-robot decision-making problem might treat the human's actions and instructions as extra state information. However, we recognize that the human's actions, instructions, and their internal reward system are interconnected. When humans act and give instructions, they are essentially trying to maximize a hidden reward function that the robot cannot see. To address this, we propose to explicitly model the unobserved variables that represent the human's goals and intentions. This allows us to better interpret the human's actions and clarify the instructions by understanding the task they want the robot to perform. We start by assuming that the human's reward functions can be linked to a set of potential goals. At the beginning of each episode, the human's goal is chosen from this set and remains constant throughout the interaction, although it is not directly visible to the robot. These goals are often broad and complex, like organize the bedroom. We assume that the human's actions are rational and aimed at maximizing their reward based on their chosen goal. As the human progresses, they select a specific subgoal for which they want the robot's assistance, such as put all books in the box, and then they provide a task for the robot to execute, like handing over a specific book. The instruction given to the robot is based on this task. We illustrate the relationships between these variables and define a set of predicates that classify states, indicating whether certain conditions are met. For instance, one predicate could describe the action of putting all books into a box. We assume that the human's goal consists of a set of these predicates, and they work on them sequentially, stopping at a certain point to choose a subgoal from the remaining predicates. Next, the human specifies a task for the robot that will lead to a state where the reward is positive concerning the chosen subgoal. However, the robot only has access to the natural language instruction and not the specific subgoal or task details. Our model, FISER, builds on this framework by incorporating two phases of reasoning. In the first phase, we focus on task recognition, where the robot must interpret the natural language instruction into a task it can understand and execute, based on the current state and historical actions. We aim to estimate a function that maps the current state, historical actions, and instruction to the robot's task. In the second phase, we propose a method to estimate the human's overall plan based on their actions and use this information to clarify the instruction. Since fully recognizing the plan can be complex, we also consider the instruction and current state to predict the specific subgoal the human wants the robot to assist with. Thus, we develop two functions, one for recognizing the subgoal and another for determining the corresponding task for the robot. Section Summary. In this section, we model human intentions in human-robot interactions by recognizing the correlations between a human's actions, their internal reward function, and the instructions given to the robot. We propose a framework that allows the robot to disambiguate these instructions by estimating both the human's subgoal and the specific task for the robot, leveraging the human's trajectory and the context of the interaction. Section: Embodied Reasoning, Grounded Planning. In this section, we discuss embodied reasoning and grounded planning. Once we have the robot's goal, we simplify the task to focus on grounding and planning. We can substitute the unclear natural language instruction with the precise robot goal. Our grounded planning function, GP, should ensure that when we input the current state, the human's trajectory, and the robot goal, it leads to the robot's actions from that point onward. This involves learning a goal-conditioned policy for the robot. Since the functions for tracking the human's intentions and recognizing their plans rely on natural language, we need language models for these components. For GP, we can use either planning algorithms or neural networks, as all inputs can be represented symbolically. Next, we implement a transformer-based model according to our framework. We assume all inputs are in text form, and the model's task is to predict action strings. Given that smaller language models struggle with long inputs, we break the information into four parts: the world state description, the human's trajectory, the language instruction, and the model's past outputs. For the world state description, we adopt an object-centric approach, representing the world as a sequence of object tokens. Each object token combines information about the object's type, attributes like size and color, and its spatial relationships with other objects. We also treat the human and the robot as special objects. To represent the human's trajectory, we describe the action sequence in text, such as, the human picks up book number 1 from the table. We replace object names with the corresponding object tokens from the world state description for better alignment. The language instruction is tokenized and converted into embeddings. For the model's past outputs, we gather sentences that describe the effects of the agent's actions, concatenating them for each episode. This helps the model understand its previous actions and any changes in the world state. Our model architecture includes 3 times n encoder layers, where n equals 3, to process all 4 input parts and predict the human's intentions or the robot's actions. We use embeddings from a specific layer to predict the robot's task and then adjust the instruction input for the next layer based on this prediction. If we include human plan recognition, we predict the human subgoal and update the trajectory input accordingly. We can train the model in either a multi-staged or end-to-end manner. The end-to-end models directly output the robot's actions, while the multi-staged models separate social reasoning from embodied reasoning, training them as distinct modules. Each encoder layer consists of 4 transformer layers and a modality interaction module. We use 4 separate transformer layers to process the inputs, omitting positional encoding for the world state description since we do not need to learn the order of objects. To integrate information from the 4 input parts, we design a modality interaction module within each layer, using a special interaction token to facilitate communication between the parts. The updated tokens replace the original first token in each input section. Section Summary. In this section, we outline our approach to embodied reasoning and grounded planning for robots, where we convert natural language instructions into precise robot goals and utilize a transformer-based model to process various input components, including world state, human trajectory, language instructions, and past outputs. Our model architecture employs multiple encoder layers to predict robot actions and human intentions, integrating information through a modality interaction module to enhance the decision-making process. Section: Prediction Layers. In this section, we introduce our predictors for the intermediate reasoning steps and final actions. All predictions are trained using cross-entropy loss based on the relevant supervision. For social reasoning regarding human plan recognition, we assume there is a set of concepts that helps us express human goals as logical statements. We simplify this by assuming human plans consist of a quantifier, a subjective, a verb, and an objective. Thus, our model's plan recognition module predicts a tuple of these 4 tokens, relying on the embeddings of the 4 inputs. In terms of robot task recognition, our main goal during the social reasoning phase is to identify the specific task assigned to the robot, such as which object to manipulate. Here, we focus on concrete objects rather than just object types. For embodied reasoning, we need to predict the next action, which we define as a combination of an action type and 1 or 2 arguments. The prediction of the action type is based on the embeddings of the 4 inputs, while the arguments depend on the predicted action type. We calculate the likelihood of all actions and select the best applicable action based on the maximum likelihood. We evaluate our framework by training a transformer-based model from scratch on the challenging HandMeThat benchmark and comparing it with various competitive baselines, including state-of-the-art methods and the largest pre-trained language models. We will test 2 main hypotheses. First, that explicitly modeling human intentions is more effective than directly predicting actions, and second, that pre-trained language models, despite their common sense knowledge, struggle with complex social and embodied reasoning tasks, but incorporating domain-specific knowledge can help. We assess our models using the HandMeThat version 2 dataset, which presents a household instruction following task in text form. The tasks are categorized into 4 difficulty levels, with increasing complexity. Level 1 tasks are straightforward planning tasks, while Level 2 requires social reasoning based on human actions. Level 3 introduces pragmatic reasoning, where context helps clarify ambiguous requests. Finally, Level 4 tasks involve inherent ambiguities that may be resolved with prior knowledge of human preferences. We evaluate all models based on their success rates in achieving the robot's goals, noting that the original HandMeThat metric also considers the number of steps taken by the robot. We believe that a realistic approach does not involve exhaustive searching, so we limit our experiments to a single trial, aiming to complete tasks within 4 or 5 steps. Section Summary. In this section, we introduce our predictors for intermediate reasoning and final actions, trained using cross-entropy loss, while outlining our approach to human plan recognition and robot task recognition through a structured tuple of tokens. We evaluate our framework on the HandMeThat benchmark, exploring hypotheses about the effectiveness of modeling human intentions and the limitations of pre-trained language models in complex reasoning tasks. Section: Baseline Models. In this section, we compare our results to human performance on the task, a hand-coded baseline that uses true symbolic state information, and a neural network baseline from the HandMeThat paper. The existing state-of-the-art work was based on the original HandMeThat dataset, so we also report our FISER model's results on version 1 data points that fit within the version 2 domain. More details about this comparison can be found in the appendix. We implement a series of transformer-based models following our proposed architecture. We compare models with no intermediate supervision, those using only robots' task recognition, and those that also include humans' plan recognition. Our models are trained from scratch since existing small pre-trained models cannot manage the long input sequences from HandMeThat data. We explore two training methods for the transformer-based model using the FISER framework, end-to-end and multi-staged. This comparison helps us understand whether blocking the gradient flow from embodied reasoning to social reasoning is beneficial. We also report the accuracy of intermediate predictions for these models, including simplified human subgoals and specific objects to manipulate. The end-to-end model has 5.1 million parameters, while the multi-staged model has 4.7 million parameters, divided into social reasoning and embodied reasoning components. We develop prompting methods for GPT-4 Turbo for HandMeThat tasks. The basic implementation provides all inputs to the model and asks for actions. We first enhance the prompts with domain-specific knowledge to help interpret complex inputs. Then, we apply the FISER framework using chain-of-thought prompting to predict the same intermediate data step by step, resulting in two models, one with FISER and one with both FISER and plan recognition. In both social reasoning steps, we prompt GPT-4 for step-by-step reasoning but ask different questions for human and robot recognition. We also consider filtering out irrelevant objects to see how it affects GPT-4's reasoning. The prompts for GPT-4 Turbo are detailed in the appendix. We evaluate all models on the HandMeThat version 2 dataset in a fully observable setting. Our best-performing transformer plus FISER model achieves a 64.5% success rate on average, marking the state-of-the-art on the HandMeThat benchmark. The main results are summarized in a table. Now, we discuss our hypotheses. First, we find that explicitly modeling human intentions is more effective than directly predicting actions. Separating social and embodied reasoning by recognizing the robot's task improves success rates across all difficulty levels, supporting our hypothesis. The comparison of different training methods shows that multi-stage training outperforms end-to-end training, suggesting that low-level planning requires a different task representation than inferring human goals. This supports the idea that we should make explicit inferences about human intentions as intermediate steps. Second, we see that recognizing the human's plan aids the social reasoning stage. Including the human's plan recognition stage helps mainly in the most ambiguous cases. For GPT-4 Turbo, adding plan recognition yields similar performance to the standard FISER method. We believe this is because pre-trained language models struggle to use hierarchical predictions effectively. For transformer-based models, adding plan recognition improves performance on the most complex tasks but hinders performance on simpler tasks. This suggests that simple tasks do not need high-level goals, and forcing the model to predict this information can distract from planning low-level actions. However, the improved performance on complex tasks indicates that recognizing human plans helps the model learn about human intentions better, allowing it to take more effective actions even in ambiguous situations. Section Summary. In this section, we compare our FISER models against human performance, a heuristic baseline, and a neural network baseline, while also exploring various transformer-based models with different training approaches. Our results indicate that explicitly modeling human intentions and separating social from embodied reasoning significantly enhances performance, particularly in complex tasks, with our best transformer plus FISER model achieving a state-of-the-art success rate of 64.5% on the HandMeThat benchmark. Section H2. Pre-trained LLMs, despite having access to common sense knowledge, do not adequately perform the complex social and embodied reasoning in this task. Incorporation of domain-specific knowledge through COT can help. In this section, we discuss how pre-trained large language models, LLMs, despite having access to common-sense knowledge, struggle with complex social and embodied reasoning tasks. We find that incorporating specific domain knowledge through chain of thought, COT, techniques can enhance performance. Our results indicate that training smaller, more efficient transformer-based models from scratch leads to about a 70% improvement compared to using state-of-the-art pre-trained LLMs. When we evaluate GPT-4 Turbo on level 1, it shows some ability for embodied reasoning when given clear tasks. However, its performance declines in subsequent levels, suggesting that common-sense knowledge alone is insufficient for solving HandMeThat tasks. With well-crafted prompt engineering that includes domain knowledge and examples, GPT-4 Turbo performs significantly better across all levels. Yet, it still lags behind smaller transformer models. We also analyze the failure cases for the FISER framework when prompting GPT-4 Turbo and training transformer models. We define several failure modes. Planning failure, where the model fails to locate the target object or takes invalid actions. Redundant behavior, where it provides an object already at the target location. And incorrect intention, where the model's reasoning does not align with human goals. For instance, GPT-4 might pick a radish for soup preparation, even if that's not the human's intention. Our findings show that while transformer models can avoid planning failure and redundant behavior, accurately identifying the target object remains a challenge. We note that GPT-4 Turbo has a planning failure rate of about 20%, consistent with its 80% success rate on level 1, which focuses solely on embodied reasoning. We believe that the limitations of GPT-4 Turbo stem from its prompting methods, which do not adequately support the social and embodied reasoning needed for this task. Additionally, the knowledge gained from online language datasets may not align with the requirements of household assistance tasks. To further investigate, we conducted an experiment to see if we could improve the performance of pre-trained LLMs by filtering out irrelevant objects from the environment, assuming we had access to the true human goals. The results showed that even with only relevant objects, GPT-4 Turbo achieved less than an 85% success rate, reflecting its planning failure rates. As the number of irrelevant objects increased, its success rate dropped significantly, highlighting the challenges of social reasoning in HandMeThat tasks. In summary, we observe that the performance of LLMs heavily depends on filtering out a large number of objects, indicating that they struggle to select and focus on relevant information necessary for effective embodied reasoning.